Let's take a look at the second part to Unit 1, which is on mass spectroscopy of the elements. So the learning objective is to be able to explain the relationship between the mass spectrum of the elements and the masses of that element's isotopes. And two pieces of knowledge you need for this are that mass spectrums allow us to determine the isotopes of an element and their relative abundance. And secondly, that the average atomic mass is the weighted average of all of those isotopes by relative abundance. And the reason this is important is it's going to show us how we get those atomic masses that we use for molar masses. So let's start off by defining mass spectroscopy. And it's this analytical technique that uses magnetic fields to push ionized particles. And this is going to allow me to separate them and count them. And what it's going to allow me to do is to detect isotopes. And remember that isotopes are atoms of the same element, but they have a different number of neutrons. So here are 3 isotopes of hydrogen. They all have 1 proton, which is how we define hydrogen, but they have a different number of neutrons, and that means each of these has a different mass. 1 atomic mass unit, 2, 3, roughly. And so the heaviest is hydrogen 3. Now, what a mass spectrometer does is it uses an ionizer to remove all of the electrons of the atom and send it through a magnetic field. And as it goes through the magnetic field, it's going to get pushed by the magnet. The heavier the atom is, the harder it is to change the trajectory of the atom, and we can get different outcomes based on how much we push. We can change that magnetic strength, and we can also get different outcomes on where they come out. And this allows us to control which particles are going to make it to our detector. So I can show you what this looks like in a simulation. Here is a mass spectrometer simulation that's currently running. And there are 3 types of particles here. They're color-coded. The red ones are the biggest, the green ones are in the middle, and the blue ones are the smallest. And right now, my magnet is set to the weakest. And so my magnet is allowing the blue ones to be detected, and only the blue ones. The magnet's not strong enough to cause the red ones to bend, so they're hitting the wall before they can bend. The green ones are bending, but not enough to go into the slits, which are in the middle here. So they're hitting the wall of these little slits. If I increase the magnet strength, now my blue ones are going to bend too much and they're going to hit the bottom of these walls. My green ones are bending just the right amount, and so they're being detected. And now the red ones are making it around the corner, but they're hitting the top of the walls. And then finally, if I make the magnet all the way strength, or at high strength, my blue ones are bending so much that they don't make the corner. My green ones are now hitting the bottom because they're bending too much. And the red ones are just the ones that are on the trajectory to hit the detector. So in this way, I can see what isotopes are there, what the masses are, and by knowing the magnetic strength, I just do some math to figure out those masses. And this is the way a mass spectrometer works. So a mass spectrometer is going to allow me to get the average atomic mass because I'm going to be able to get the relative abundance, what percentage of each isotope there is, and I'll know the mass of those isotopes. And if I know those 2 things, all I have to do is multiply the mass of the isotope by the relative abundance, and I do that for every isotope, and I add them up, and I'll get these atomic mass numbers. And we're going to practice this in other videos, and we're going to look at what these spectrum look like so you can see what the data looks like when they come out.